Chapter 3 continued, Stoichiometry of Formulas and Equations, Section 3.1, the mole. The mole, abbreviated MOL, is the SI unit for the amount of a substance. The mole is often referred to as the chemist's dozen. The mole is defined as the amount of substance that contains the same number of entities as there are atoms in exactly 12 grams of carbon-12. The term entity can refer to atoms, ions, molecules, formula units, electrons, or any other particle. 1 mole of any particle is equal to 6.022 times 10 to the 23 entities up to 4 significant figures. This number is called Avogadro's number, and it is abbreviated with an uppercase N. There are 12 eggs in a dozen, and there are 6.022 times 10 to the 23rd eggs in 1 mole of eggs. 1 mole of carbon-12 atoms contains 6.022 times 10 to the 23rd moles of carbon-12 atoms. 1 mole of hydrogen bromide contains 6.022 times 10 to the 23rd moles of hydrogen bromide formula units. The mole is a very convenient way of expressing the enormous number of molecules or ions that take part in chemical reactions. This slide shows 1 mole of some familiar elements and compounds. 1 mole of copper pellets has a mass of 63.55 grams, and 1 mole of water weighs 18.02 grams. The other substances shown here include a mole of sodium chloride, table salt, a mole of sugar cubes or sucrose, and a mole of aluminum foil formed into a ball. The molar mass of a substance is defined as the mass of 1 mole of entities, atoms, molecules, or formula units of a substance in units of grams per mole. This slide summarizes the mass terminology that we will be using throughout this course. We already know about the mass of isotopes and how to calculate the atomic mass or atomic weights. Now we are going to see how to calculate the masses of molecules, compounds, and ions. Before we learn how to calculate the mass of compounds and molecules, we first need to start with the elements. As you will soon learn, the periodic table is going to be the source of valuable information that we will use over and over again. We will use the periodic table to calculate molar masses. For monoatomic elements such as sodium, iron, argon, the molar mass is the numerical value from the periodic table expressed in units of grams per mole. Therefore, the molar mass for sodium is 22.99 grams per mole, for iron 55.85 grams per mole, and for argon 39.95 grams per mole, and the molar mass for neon is 20.18 grams per mole. For molecule elements, we need to know the molecular formula in order to determine the molar mass. For example, oxygen exists as a diatomic molecule, so the molecular formula for oxygen is O2. The molar mass of diatomic oxygen is twice that of an oxygen atom. The molar mass of diatomic oxygen is determined by multiplying the atomic weight of oxygen by 2. So 2 times 16.00 equals 32.00 grams per mole. The molar mass of sulfur dioxide can be found by multiplying 2 times the atomic weight of oxygen and adding it to the atomic mass of sulfur. Therefore, the molar mass of sulfur dioxide is 64.00 grams per mole. So in summary, to find the molar mass of water, you multiply the atomic weight of each element in the molecular formula by the number of times it appears in the formula. Remember, the subscripts in the molecular formula tell you how many of those atoms are present in the formula, as well as how many moles of atoms are present. This slide illustrates the type of information that can be found in a chemical formula. The compound here is glucose, which is the essential sugar in energy metabolism. Please notice that 1 mole of glucose that has the chemical formula CH812O6 contains 6 moles of carbon atoms, 12 moles of hydrogen atoms, and 6 moles of oxygen atoms. This relationship between atoms in a molecular formula and the molecular formula will become very important in later chapters. One of the most important conversions you will need for this course, and probably use the most, is the conversion of grams to moles and moles to grams. Another important conversion is the conversion of moles of substances to entities of that substance. This slide illustrates the strategies behind these two very important conversions. To convert moles to grams, you multiply by the molecular weight expressed in grams per mole. Remember the lecture from chapter 1, the units you want to cancel will appear in the denominator, and the units you want to end up with will end up in the numerator. To convert grams to moles, you divide by the molecular weight expressed in grams per mole. We can also use Avogadro's number to convert between moles and entities, such as atoms, molecules, or formula units. To convert moles to entities, you multiply by Avogadro's number, which you remember is 6.022 times 10 to the 23rd, where the units are expressed in entities per mole. There are no units associated with Avogadro's number until you want to express the number of entities 1 mole of the substance contains. To convert between the number of entities in moles, you would divide by Avogadro's number. This is a summary slide that shows the mass-mole number relationships for elements. The number of moles of an element is related to its mass in grams through the molar mass with units of grams per mole, and to its number of atoms through Avogadro's number with units of atoms per mole. For elements that occur in molecule, the unit for Avogadro's number will be molecules per mole. When working problems involving mass-mole number relationships of elements and compounds, keep these points in mind. To convert between mass and moles, use the molar mass with units of grams per mole. To convert between moles and numbers of entities, use Avogadro's number 6.022 times 10 to the 23rd with units of entities per mole. For elements that occur as molecules, use the molecular formula to find atoms per mole. Mass and numbers of entities relate directly to the number of moles, not to each other. Therefore, to convert between numbers of entities and mass, first convert to the numbers of moles. The best way to illustrate a new concept is to work an example, so let's work through sample problem 3.1, which is on the next slide. This is sample problem 3.1, and it is designed to give us practice converting between grams and moles. The problem is asking us to find the number of grams of silver present in 0.0342 moles of silver. Getting used to reading word problems and determining what you are asked to do is a very important skill you would want to develop for this course. You need to develop a strategy for solving problems such as this one. Ask yourself, what is the problem asking me to do? By asking yourself this question, you will hopefully determine what the conversion factor you will need in order to solve the problem. In this problem, we are asked to convert moles to grams of an element. To convert moles to grams, we need the molar mass of silver. Once we have the molar mass of silver with units of grams per mole, we are ready to convert moles to grams. Remember, we have units of moles and we want to have units of grams. Therefore, grams need to be in the numerator and moles need to be in the denominator. The molar mass of silver is found by locating silver on the periodic table. Setting up the problem and solving for grams, we find that there are 3.69 grams of silver in 0.0342 moles of silver. Be sure to record your final answer with the correct number of significant figures. Please work through the follow-up problem before moving on to the next slide. Sample problem 3.2 was a little different. We are given moles of gallium and asked to find how many gallium atoms are present in 2.85 times 10 to the negative third moles of gallium. Remember, to convert moles to atoms or any other entity, we need to use Avogadro's number. Our plan is to multiply moles of gallium by Avogadro's number in order to find the number of atoms of gallium. Try to do the math for yourself before moving on to the next slide. You will also need to remember how to enter exponents into your calculator. If you do not know how to enter exponents on your calculator, please look this information up in your owner's manual. If you do not have a copy of your owner's manual, most owner's manual can be found at the website for your brand of calculator. Please let me know if I can help you as well. As you can see here, the correct answer is 1.72 times 10 to the 21st atoms of gallium. Were you able to come up with the correct answer? If yes, great job, and please go on to the next slide. If no, can you see where you may have made a mistake? One common error is entering of the data into your calculator. Please make sure you are entering the data into your calculator correctly. Please work through the follow-up problem before moving on to the next slide. Sample problem 3.3 is asking us to determine the number of iron atoms in 95.8 grams of iron. The strategy here is to convert grams to moles using the molar mass of iron, and then to convert moles to atoms using Avogadro's number. Remember, we cannot directly go from grams to atoms. We must convert to moles first. To perform conversions that require more than one conversion, you can set up a problem like the author did in this example, where grams were converted to moles and then moles were converted to atoms in 2 steps. If you do it this way, you will want to carry extra significant figures along the way to avoid what is known as accumulated rounding error. You do not want to round to the correct number of significant figures until all calculations have been completed. The other way is to string the conversions together and do the calculations in one step. With this method, you avoid the possibility of accumulated rounding error. So our plan is to convert grams of iron to moles of iron and then convert moles of iron to atoms. To convert grams to moles, we need to divide by the molar mass of iron. Remember, the molar mass of any element can be found on the periodic table located on the front jacket of your book. Now we have moles of iron. To convert moles of iron to atoms of iron, we need to multiply by Avogadro's number. Make sure you record your final answer in the correct number of sig figs. The exponent is not counted when determining sig figs. Please work through the math before moving on to the next slide. So starting with 98.5 grams of iron, we would divide by the molar mass of iron, which is 55.85 grams per mole, and then we could convert moles of iron to atoms of iron by multiplying by Avogadro's number to get the value that you see here. Remember, rounding to the correct number of significant figures, we obtain the answer of 1.04 times 10 to the 24th iron atoms. When the conversion requires more than one step, you may do each step individually or combine the conversions into one step. If you prefer to do steps individually, be sure to carry extra significant figures to avoid accumulated rounding error. Don't forget to work through the follow-up problem on your own. Be sure to seek help if you have any trouble working through any of the follow-up problems. Remember, the answers to all follow-up problems can be found at the end of the chapter, right before the end of the chapter problems. This slide summarizes the mass-mole number relationship between compounds. Solving mass-mole number problems for compounds require a very similar approach to the one for elements. We need the chemical formula in order to calculate the molar mass, which is needed to find the number of moles of a given element in the compound. The relationships are shown here. Moles of a compound are related to grams of the compound through the molar mass with units of grams per mole, and to the number of molecules or chemical formulas through Avogadro's number with units of molecules per mole. To find the number of molecules or formula units in a given mass or vice versa, we need to convert to moles first. With the chemical formula, you can calculate the mass-mole number information about each component element. Again, to help cement this concept, let's work through a problem. In this sample problem, we are asked to determine how many molecules are in 8.92 grams of nitrogen dioxide. First thing we will need to determine in our plan to solve this problem is determine the chemical formula from the name of the substance. This is a very important skill we need to master early on in this course. Once we have the chemical formula, we can calculate its molar mass. We need to have the molar mass in order to convert grams to moles. Once we have moles of nitrogen dioxide, we can convert moles to molecules by multiplying by Avogadro's number. Okay, that is our plan in solving this problem. Please work through the problem before moving on to the next slide where you can check your work. If you get stuck at any step along the way, please email me using the email system built in the course, and I will send some help as soon as I can. It would be very helpful to me if you would include your work in your email to me so I can try to figure out where you were going off track. Let's work through the solution for this problem a little slower. If you obtain the correct answer and do not have any questions or concerns, please move on to the follow-up problem before moving on to the next slide. If you did have some difficulty solving this problem, let's see if we can help you figure this type of problem out. First off, we need to come up with the correct chemical formula for nitrogen dioxide. Since both nitrogen and oxygen are nonmetals, this is a covalent compound. Since nitrogen is listed first without a prefix, we know we only have one nitrogen atom in the formula. Dioxide indicates we have two oxygen atoms in this molecule, so the formula for nitrogen dioxide is NO2. Now that we have the chemical formula, we need to calculate its molar mass. To find the molar mass, multiply the number of times each atom appears in the formula by its molar mass. To find the molar mass of nitrogen dioxide, multiply 1 mole of nitrogen by its molar mass of 14.01 grams per mole, and add it to 2 times the molar mass of oxygen, which is 16.00 grams per mole. Therefore, the molar mass for this molecule is 46.01 grams per mole. Now we have the molar mass, we can convert grams to moles by dividing by the molar mass. Finally, we can convert moles to molecules by multiplying by Avogadro's number. The final answer should be 1.17 times 10 to the 23rd molecules of nitrogen dioxide. Remember to record your final answer in the correct number of sig figs. Since the starting data of 8.92 grams contains 3 sig figs, so must our final answer. Be sure to work through the follow-up problem before moving on to the next slide. Our next sample problem wants us to determine the number of formula units that are in 41.6 grams of ammonium carbonate in Part A. In Part B, we need to find the number of oxygen atoms in the sample. What is our strategy for Part A? We need to convert grams to formula units, and we know we cannot do this directly. First, we need to determine the chemical formula for ammonium carbonate and then determine its molar mass. Once we have the molar mass for the compound, we can determine the number of formula units. Then we can go on to Part B. In Part B, we are asked to determine the number of oxygen atoms in this compound. To do this, we need the number of formula units found in Part A and the chemical formula for this compound. So our strategy is to convert grams of ammonium carbonate to moles of ammonium carbonate by dividing by the molar mass of ammonium carbonate. Then we can convert moles of ammonium carbonate to formula units of ammonium carbonate by multiplying by Avogadro's number. This will give us the number of formula units of ammonium carbonate. Then we can find the number of oxygen atoms simply by multiplying the number of formula units by the number of oxygen atoms in the compound. So we need the chemical formula for ammonium carbonate. If you cannot remember the structures for these polyatomic ions, please go back to Chapter 2, Section 2.8. The chemical formula for the ammonium ion is NH4+, and the chemical formula for the carbonate ion is CO3 2-. Now use the crossover method to determine how many ammonium ions you need to balance the charge. The formula for ammonium nitrate is start parentheses NH4 end parentheses 2 CO3. You need to remember to put the ammonium ion in parentheses with the 2 subscript on the outside of the parentheses. Now that we have the chemical formula for ammonium carbonate, we can calculate the molar mass of ammonium carbonate. Even though the calculations for the molar mass for this compound are given to you on this slide, try working through the math to see if you can come up with the correct mass before moving on to the next slide. If you are having troubles with calculations, the molar mass of ammonium carbonate is found by taking 2 times the molar mass of nitrogen plus 8 times the molar mass of hydrogen plus 1 times the molar mass of carbon plus 3 times the molar mass of oxygen to get 96.09 grams per mole as the molar mass of ammonium carbonate. If you have any questions about this, please contact me. Now we have everything we need to convert grams to moles and then moles to formula units of ammonium carbonate and to find the number of oxygen atoms. So let's set this up. Start with the mass in grams that was given to us in the problem, which was 41.6 grams, and divide this by the molar mass to get moles of ammonium carbonate. The moles of ammonium carbonate are then multiplied by Avogadro's number to get the number of formula units of ammonium carbonate in 41.6 grams of this compound. Once you have the number of formula units, multiply by 3 to get the number of oxygen atoms. Try to work through the problem before moving on to the next slide. Hopefully you found the number of formula units to be 2.61 times 10 to the 23rd formula units of ammonium carbonate rounded to the correct number of sig figs, and the number of oxygen atoms to be 7.83 times 10 to the 23rd oxygen atoms. If you got the correct answer, great job. If not, please work through the problem again and let me know if you need more help. To get more practice, work through the follow-up problem and let me know if you are having any troubles with the conversions of grams to mole and moles to entities or vice versa. We are able to determine what fraction of mass each individual element contributes to the overall mass of the compound. This is known as the mass percent. To find the mass percent of any element in a compound, you take the number of times the atom of the element of interest appears in the chemical formula and multiply it by its atomic weight. Remember, the units of atomic weight or mass is AMU. Then you divide this number by the total mass of the compound with the mass expressed with units of AMU. Then multiply by 100 in order to convert the number from a decimal to a percent. We can also determine the mass percent of each element in the compound on a mole basis by using the molar mass of the element of interest and the molar mass of the compound. The calculations are the same as finding the mass percent of an element with units of AMU. So let's do a couple of examples. This sample problem wants us to determine the mass percent of each element in ammonium nitrate, which is used by farmers as a fertilizer. So what is our strategy? We need to find the mass percent of the elements present in 1 mole of ammonium nitrate. Therefore, we need to come up with the formula for ammonium nitrate, and then we need to calculate the molar mass of ammonium nitrate. Remember how to calculate molar mass? You multiply the number of times each atom appears in the chemical formula by its molar mass with units of grams per mole. Once we have calculated the molar mass, we can find the mass percent of each element by dividing the mass of that element by the total mass of 1 mole of ammonium nitrate. Okay, here is our roadmap for our plan for solving this type of problem. We know the relative amounts in moles of the element from the chemical formula. Now we have to find the mass percent. To do this, we multiply the amount of each atom by its molar mass to find its mass. Then we divide each mass by the total molar mass of the compound to find the mass fraction of each element. Multiplying the mass fraction by 100 gives the mass percent of each element. Okay, try this on your own before moving on to the next slide where you can check your work. If you are stuck, move on to the next slide for more help. Here is the chemical formula for ammonium nitrate. Now we need to find the molar mass for ammonium nitrate by taking all the numbers of each atom times its molar mass and then add them all together to get the molar mass. Hopefully you found the molar mass to be 80.05 grams per mole. As mentioned in the book, you should be able to calculate molar masses for any compound given to you. From this point on, it is expected that you will be able to calculate molar masses, and the calculations will no longer be discussed when working problems. Please let me know if the calculations of molar masses is causing you any difficulty. Now that we have the molar mass of ammonium nitrate and the masses of each element in ammonium nitrate, we can calculate the mass percent simply by dividing the mass of the element by the mass of ammonium nitrate and then multiplying by 100. Okay, so here we have the mass percent for nitrogen and hydrogen, and on the next slide we will find the mass percent for oxygen. Here you can check your answer for the mass percent of oxygen. Any questions, please let me know, and please remember to work through the follow-up problem before moving on to the next slide. We can also use the mass percent to find the mass of an element. To find the mass of an element in a sample, take the mass of the compound, divide it by its molar mass, and multiply it by the total mass of the element of interest. To see if we understand how to find the mass of an element from the mass percent, let's work through a sample problem. In case you haven't already noticed, the best way to understand the concepts in chemistry is to work problems. This is also the best way to prepare for the weekly quizzes and for the exams. The more problems you work, the better prepared you will be to take the quiz or the exams. Our next sample problem wants us to use the information in the previous sample problem to find the mass of nitrogen present in 650 grams of ammonium nitrate. We know the molar mass of nitrogen and we know the molar mass of ammonium nitrate. We can use this as a conversion factor in order to calculate the mass of nitrogen in this new mass of ammonium nitrate. So basically we are starting with the new mass of ammonium nitrate and using the molar mass of nitrogen over the molar mass of ammonium nitrate as a conversion factor. Try this on your own before checking your work on the next slide. Hopefully you were able to come up with the same answer as shown here. If yes, great job. If no, can you see where you may have gone off track? Remember to email me if you are having any trouble with any of the sample or follow-up problems.